Hello, and welcome to another edition of Mr. Chappell's Chemistry Screencasts. Today we're going to learn about dealing with violations of the Octet rule. What you'll learn today is how to draw Lewis dot diagrams for compounds that violate the Octet rule. Now there are a couple of things you're going to need. You're going to need a periodic table, and you're going to need the Lewis dot diagram procedure. Let's go ahead and get started. Okay, here are our first examples, and the first one is a boron hydride, and our first step is, of course, to go ahead and add up all the electrons that we have in the compound. And let's see, we've got one boron, and one boron contains a total of 3 electrons, and we've got 3 hydrogens. And so that's going to be 3 times 1 electron. And so when I add all these up together, I get 6 electrons. Well, I already know there's going to be a trouble in River City because I don't have 8, and it's hard to give an octet if you only have 6. For step 2, this is really just about the only trial structure possible. For step 3, our accounting step, we started with 6 electrons, and we've got 2, 4, 6 electrons in our trial structure. And, well, darn it, that leaves us with absolutely nothing to put down. And we just kind of have to be okay with that. Boron is kind of the classic example of an electron-deficient compound or element. And, yeah, there's not much you can do about that. Boron's the most common one, but there are others. Now, the rest of these examples focus on expanded octets. Okay, the first one is xenon tetrafluoride, and our first step is to add up the electrons. So we've got 1 xenon, and you can already tell there's going to be trouble because xenon is an inert gas and really shouldn't be combining with anyone, but, you know, with fluorine it can be made to do that. So we've got, it's going to be 1 times 8 electrons in its valence shell. And then we have 4 fluorines. And so that is going to be 4 times 7 electrons. And be careful with your addition. These always have a lot of electrons. Let's see, this gives us a total of 36 electrons. For our trial structure, well, let's go ahead and put xenon in the middle. And for our counting step, step number 3, we started with 36 electrons. And we have 2, 4, 6, 8 electrons in our trial structure. And so that means we have a whopping 28 electrons that we have yet to put down. So let's go ahead and do that. So for step 4, let me recreate the trial structure. And let's go ahead and give each of the fluorines an octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, well, everyone's got an octet, but we still have 4 electrons we have to put down. And so our choices are, well, either put them down with the fluorine or put them with the xenon. Well, fluorine, being a second period element, does not have any room for extra electrons, period. Whereas xenon does. He has a lot of empty orbitals, so let's go ahead and put him down with xenon. And this has the added advantage of having no formal charge on the xenon when you're done. And, well, that's it. That's an expanded octet. For our next example, this is bromine pentafluoride. And let's go ahead and add up the electrons. We've got 1 bromine, and that's going to be 1 times 7 electrons. And we have a total of 5 fluorines, and so that's going to be 5 times 7 electrons. And so that ends up being 42 electrons. For step 2, well, let's see. Looks like bromine's going to be in the middle of things, just to keep everything symmetrical. So we'll put the fluorines all the way around it. And for step 3, our counting step, well, we started with 42 electrons. And we have 2, 4, 6, 8, 10 electrons there. Which means that we are missing a total of 32 electrons. And that's a lot of electrons. So for step 4, let me go ahead and reproduce the trial structure. And each of the fluorines is going to need a total of 6. So let's go ahead and start giving octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, everyone's got 8, but unfortunately, we have to put down 2 more electrons, and your choices are fluorine or bromine. Well, bromine's going to have the empty orbitals to handle it. Fluorine is just not going to have that, so those extra electrons go down just like so. And so that becomes our final answer. And since I'm here, I forgot to circle this as being our final answer too on the previous problem. And that's how you do it. For step 1, let's see, we've got 1 xenon, and that's going to be 1 times 8 electrons. We have 2 oxygens, that's going to be 2 times 6 electrons. And for fluorine, we've got 4 of them, and that's going to be 4 times 7 electrons, and that's going to give us a total of 48 electrons. For step 2, let's go ahead and put xenon in the middle. And let's go ahead and put the oxygens at opposite ends, although that doesn't really matter. For step 3, well, we started with 48 electrons, and it looks like we've got 2, 4, 6, 8, 10, 12 electrons there, which means that we are missing a whopping 36 electrons. So for step 4, let's go ahead and put them there. But first we have to reproduce the trial structure. And here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, and 36. And there you go. Now, there is one alternate to this trial structure, and that includes having double bonds that go. This is a kind of a Whoops, this is kind of a step 5 example. Let's see, if we get rid of 2 electrons here, erase the right thing, one disappear, and 2 here, and let's go ahead and put those back in. And what you can have as an alternate is this. And the advantage to this structure is that you don't have any formal charges. If you leave the double bonds off, then you're going to have a formal charge on the xenon, a big one, positive 2, and formal charge on each of the oxygens. Whereas with this, you get nothing. There's no formal charges. Okay, for our last example, this is xenon hexafluoride. And so let's see, we've got 1 sulfur. So that's going to be 1 times 6 electrons. And we've got 6 fluorine, so it's going to be 6 times 7 electrons. Well, let's see, that's going to be 42. That's going to be 48 electrons again. For the trial structure, well, we don't have a lot of options. So let's just go ahead and put everything on the sulfur. For step 3, well, let's see, we started with 48 electrons. And if you look very closely there, we've got a total of 12. This should start looking really similar to the one we just did. And that means we've got 36 electrons left over. So for step 4, let's go ahead and put them there. First, we've got to reproduce our trial structure. And let's go ahead and put down our electrons. And if you are quick at math, you'll notice that, well, we've got 6 electrons that we need to put on the 6 fluorines to give everyone an octet. So that means you need 36, and that's how many you have. That way you can avoid having to count each and every time you do this. And so this is our, whoops, okay, here's our final answer for the first one, and here's our final answer for the second one. And that's how you do it, and that concludes this lesson. Okay, it's joke time again. Why do chemists like nitrates so much? Well, that's because they're cheaper than day rates. Get it? Night rate versus day rate.